In section 1.8, we're going to introduce the concept of linear transformations. To do this, we're going to think about our formula AX equals B, but we're going to look about it in a different way. So here, matrix A is an object acting on X by multiplication to produce a new vector, AX, or what we call B. So again, it's like A is going to do something to the vector X and produce a new vector. So for example, we have here is our matrix A in both examples, and we have two different vectors, call x1 and x2. And when we multiply that vector by A, we get a new vector that we call B. In this case, in the second case, the B is the 0 vector. Let's recall quickly what we mean by matrix vector multiplication. So one way to think about this is to take the row, the first row of that matrix, times the column of that vector, and you multiply the entries in a dot product like fashion. So you take the first entries and you multiply them together, 2 times 2, and then you take the second entries and you multiply them together, -4 times 3, and you add them. That gives you 2 times 2, that's 4, plus -4 times 3 minus 12 will give you a -8, which is that first entry right there. The other two entries are gotten by taking the second row times the column and the third row times the column. Another way to think about that matrix vector multiplication is to think about it as a linear combination. So for instance, we could look at the columns of A, the first one being 2, 3, 1, and the other column of A, -4, 6, -2, and we are doing a linear combination of the entries of the vector, so 2, 3, and we are adding them together, and that'll give us our B in our equation. And note that with our matrix A, if we take a different vector X, we get a different output, right? So A acts on a different vector and produces a new vector. So here we go. We're going to suppose A is an m by n matrix, and solving AX equals B, solving that equation, amounts to finding all vectors X in Rn, which are transformed into the vector B in Rm through multiplication by A. We're going to think about this as the transformation machine. This is something similar to the function machine you may have learned about in pre-calc, but we are going to input vectors X in Rn, and we are going to output vectors AX, and those vectors are in Rm. Note it's the same thing as B. So we have our inputs here and our outputs. And what's happening inside this machine is we input an X, multiply it by A does something to the vector, and we output another vector out. So let's think about this in general. A transformation T from Rn to Rm is a rule that assigns to each vector X in Rn a vector T of X in Rm. Note that this is different than what we were talking about before, because before we were just talking about multiplying by a matrix A, but a transformation T could be much more than that. It could be a lot of different things. But the same idea still applies. We are going to input vectors X, and we are going to output T of X, which is a new vector in Rm. So X is in the set Rn, n entries in that vector, and then the output is in Rm, m entries in the vector. When we are thinking about inputs and outputs, we can think about domain and range. So when we think about domain, that's going to be the set of inputs. And the range is going to be the set of outputs. But we have a new word here, codomain, that you may or may not have heard of before. And codomain is something different than range, though similar. So we're going to draw a little picture here. Let's draw a picture of a set. This is going to represent our domain. In this case, this might be Rn. And we're going to draw a set of our codomain. In this case, our codomain is Rm. Now, what's different from the codomain and the range is just a subset of the codomain where we're actually going to have outputs. So it doesn't have to be the entire codomain. It could be just a subset of it. It could be the entire codomain as well. So the idea here is that we're going to take a vector x in the domain, and it is going to get mapped to, that's our verbiage that we're going to use. This is going to get mapped to a vector t of x in our range, which is a subset of the codomain. Some terminology again. We say that t of x is an Rn is the image of x under the transformation t. We say x is mapped to its image t of x. Let's write that down too. Say that x is mapped to its image t of x. And the set of all images is going to be called the range. Let's look at these terms again with the example that we brought in the first problem. So this is going to be, our transformation is being given by multiplying by the matrix A. The rule that we're going to do is multiplying by A. And this is the example we had in our first page. We're going to identify what is the domain, the codomain, and the range of the transformation. Well, the first thing to notice is that what we're going to be doing is we're going to be taking A and we're going to be multiplying it by vectors x, and x is going to be a vector in R2, 2 entries. So when we say AX, we're going to be talking about the matrix 2, 3, 1, -4, -6, -2, times a vector x1, x2. And what that means is that this is going to be a linear combination, x1 times the first column of A, plus x2 times the second column of A. And this is our output. It's all outputs of this form, all linear combinations of those two. And another way to think about that is this is the span of those two column vectors, 2, 3, 1, and -4, -6, -2. The span here is not the codomain, but this is the range. It's our all set of outputs that we could possibly have. Note that in this example, since -4, -6, -2 is -2 times 2, 3, 1, it's a constant multiple of the other, then we can say that this is actually just the span of one of those vectors, and we'll take the easier one to deal with, 2, 3, 1. So really our range, it's the same thing, just writing it in a simpler way, is the span of that one vector. And this is geometrically a line through the origin in R3. So when we're talking about domain, codomain, range, the domain here is all of R2. You can plug in any two real numbers into x1 and x2. There's no constraints on there. Our codomain is where our outputs are going to live. They live in the realm of R3. R3. Now our outputs aren't going to be all of R3, but that's where they sort of live. And then the range is the specific part of that. That's going to be the span of that vector, which is a line in R3, only a part of it. So you could think about that we have our domain, x2, and then our codomain is all of R3, and then our range is a line that goes through the origin. And we are taking a vector x, and it's being mapped to a different vector in R3. T of x, in this case, is the same thing, ax. All right, let's do that again in a different kind of way. This time we're going to let our vector, or our matrix A, be defined by 1, 0, 2, 1, 0, 1. And we're going to define our transformation from R2 to R3 by T of x equals A of x, similar to what we did before. Note that the R2 is our domain. The R3 is our codomain. That's what that notation means. It talks about the domain going into the codomain. So the idea here is if we have a vector x, 2, 1, and we multiply that by the matrix ax, then we get a new vector out that is in R3. We take a two-dimensional vector and we get a three-dimensional vector out. Looking at the picture here, here is our vector x, 2 in the x direction, 1 in the y direction. And this corresponds to the vector 2, 5, 1. Note that in this picture right here is the origin. This is 0, 0, 0. And this is going to be the vector 2, 5, 1. We can get that picture here by going 2 over in the x direction, x1 direction, 5 over in the y direction, and then up 1 in the x3 direction. So we have our vector ax, and that's where this transformation is taken. We're taking this point, this vector, we are mapping it to that point. Now in this example, we are going to have that our range is going to be this plane in R3. Note that the plane goes through the origin. Right? This is the range, which is a plane. And how do we know it's a plane? Well, this is going to be the span of our column vectors of A. 1, 2, 0, 0, 1, 1. And we know that since these are not constant multiples of each other, we cannot simplify that span in any way. This is a span of two vectors, which gives us a plane in R3. So the domain is R2, codomain is R3, the range is as a part of it, a plane in R3. So a new example, let's let A be this 2 by 3 matrix, 1, negative 2, 3, negative 5, 10, 15. U is going to be this vector 2, 3, 1 in R3. B is going to be a vector in R2, 2, negative 10, and C is going to be a vector 3, 0 in R2. We're going to define a transformation T going from R3 to R2 by T of x is equal to AX. Again, it's this matrix multiplication that's going to define our transformation. So the first question is find an x in R3 whose image under T is B. One way to translate that sentence is what we're trying to find is we're trying to solve T of x is equal to B for x. But since t of x is just matrix multiplication, we're talking about ax is equal to b. Or putting it in terms of the matrix vector equation, we have our matrix A, our vector x, and then our vector b given in the problem. And if we're trying to find a vector x that satisfies this equation, we are solving a system of linear equations. We could write this as an augmented matrix. There are 3 columns associated with the 3 variables, x1, x2, x3. And we have an augmented matrix with the right-hand side of that bar being the vector b. If we row reduce this matrix, we get this matrix in row reduced echelon form. And if you solve that for our variables, notice that we have a pivot in the first entry there. That's the only pivot we have. We have 2 free variables, x2 and x3. We could rewrite x1 and 2 in terms of those free variables, giving x1 equals 2x2 minus 3x3 plus 2. So what we're trying to find is find a value of, or one vector whose image under T is B. There may be more than one, but we're just trying to find one, and we could pick any values of x that will work here. So for instance, we could pick x2 equals 0, x3 equals 0, and then in that case, x1 would be 2 times 0 minus 3 times 0 is 2. So in that case, we have the vector 2, 0, 0 is a vector whose image under T is B. Right? We have that A times 2, 0, 0 is 2, negative 10. Now this was just an arbitrary choice for x2 and x3. I picked 0 because they're really nice numbers. We could have picked something else, like we could have had x2 be 1 and x3 be 1. Or we don't have to have the same value. We could have x2 be 1 and x3 be 55. Any 2 numbers that you want for x2 and x3, and that can give you a new value x1. So if this was the case, we would have 2 times x2, 2 times 1, minus 3 times 55, plus 2 would be our value of 1. So the next question asks, is there more than one x under T whose image is B? We just answered that question by just giving new values of x2 and x3 that gave us a new vector that worked. And in general, since free variables exist, there are more than one x for which Tx equals B. There are infinitely many solutions to that system. And it just depends on different choices of x2 and x3. So the answer to this question is yes, there is not a unique answer, a unique vector x whose image under T is B. The next question says, determine if C, 3, 0, is in the range of the transformation. This is an existence problem. We're going to be asking, does this system have a solution? So to reword this question, we're saying, is there an x for which T of x equals C? Or we're saying that is AX equals C, is that a consistent system? Does there exist a solution? So again, we're going to be looking at the augmented matrix. This time, note that the right-hand side of our equal sign is the vector C. And if we row reduce, we get the same row reduction as we had before, but now we have different things on the right-hand side, and we get this row of zeros on the left-hand side of the bar and a 1 on the right-hand side of the bar. This corresponds to the equation 0x1 plus 0x2 plus 0x3 equals 1. That's another way of writing 0 equals 1. That's not good. That means that there are no solutions. Which means that C is not in the range of T. And here's our difference between range and codomain. C is definitely in the codomain. We can think about it in R2, but it's not in the range of T. So moving on, let's look at an application problem. Matrix transformations have many applications. In fact, linear algebra in general has a lot of applications across many fields. But one application we're going to look at is computer graphics when we're thinking about matrix transformations. So let's think about matrix transformation. We're going to be multiplying by the matrix A, which is given by 1/2, 0, 0, 1/2. This is a transformation from R2 to R2 defined by that matrix multiplication. And this is an example of a contraction transformation. And we'll look at that idea of contraction in a second. You can kind of see it in the picture already. The transformation can be used to move a point x. That's what we're doing. We're taking a point x and we are moving it in some way. So let's look at the example. Let's look at the vector 8, 6. In the picture, here is the vector 8, 6. And when we multiply by the vector A, we can think about this as doing our matrix vector multiplication. 0.5 times 8 plus 0 times 6 will give us 4. And then 0 times 8 plus 0.5 times 6 will give us 3. This is just having our entries in U. It's just dividing everything by 2. And this gets us to the entry 4, 3, which we can draw down here. This is T of U. And we could choose that for any vector that we want. So here we go. Let's do the vector 5, 0. That's going to transform into the vector 2.50. Everything's just being cut in half. Do that one more time. Everything's just being cut in half. So the way this computer graphic things works is we have a scatter plot of points. Just have a bunch of points. And we can connect those points in some way to draw a picture, in this case, a plane. And if we multiply all these vectors, all these points, by this matrix, that's the same thing as taking that image and making it twice as small. And there are lots of different vectors, lots of different matrices, I should say, that correspond to different transformations. You could scale the picture in any way. You could rotate the picture. You could move the picture. In fact, you could change the picture in any kind of way that you want, just with matrix multiplication attached to the points on this picture. Now, you might be thinking, at least I was thinking when I saw this picture, that it's not a very good plane, but that's just because we have a few points. You could get a much more detailed image of a plane by having a lot more points that we're thinking of. And those points are represented by vectors in R2 space. So now that we've talked about transformations, we're going to be talking about a more generalized thing, and that is linear transformations. Or I should say this is transformations that have a special property in the fact they're being linear. And we're first going to think about matrix multiplication. So A is m by n. Then the transformation, which is matrix multiplication, AX, has the following properties. T of two vectors added together, that's the same thing as A times those vectors added together. We talked about in a previous section that we have this property that this is AU plus AV. You can distribute that A to vectors being added together. And then since we have our definition of the transformation T, this is the same thing as T of U plus T of V. And the same thing, we have scalar multiplying by a vector, T of Cu. That's the same thing as A of Cu by our definition. And in a previous section, we talked about with matrix multiplication that we can bring that constant, that scalar, out in front. And then that means that we can rewrite that as CTU. And that's true for all vectors in Rn and all scalars C. Now that is specifically for matrix multiplication. But we can think about this in general for a linear transformation, or in fact the definition of a transformation T being linear is if those two properties hold, that T of U plus V is T of U plus T of V for all vectors in the domain, and then T of Cu equals C T of U for all U in the domain of T and all scalars C. And we can see that every matrix transformation is a linear transformation. Matrix transformation meaning that I'm going to define my transformation by multiplying by some vector or by some matrix. Now the term linear, it's in our title of our course, Linear Algebra. This has to deal with the idea of a line or a linear function. And it's the idea of if you have a linear combination of things, which we are looking at a lot in this course, then the two operations that we are doing is we are adding things together and we are multiplying by a scalar. So when you're talking about linear, you are talking about satisfying those two kind of operations. The additive property and this scalar multiplication property. So from that definition, we do get a quick result. So if T is a linear transformation, those two properties hold, then we can quickly say that T of the 0 vector is equal to the 0 vector, and T of Cu plus dV, a linear combination of two vectors, is CTU plus DTV. And we're going to prove these two things very quickly. So T of the 0 vector, we can think about the 0 vector as, so the 0 vector, let's say in R4, is just 0 times any vector that you want, as each entry just be multiplied by 0. So we're going to pick a new vector u, 0 times u, and our scalar multiplication property says that we can bring that scalar out. This time 0 is just a number, and therefore 0 times any vector tu will give us the 0 vector. Note that this is the 0 vector in Rn, and this is the 0 vector in Rm. So they might have different sizes, but it's just a vector of all zeros. A proof of the second one is going to be taking our two properties together. T of Cu plus dV, well, using the additive property, we know that this is going to be Cu and dV, T of Cu plus T of dV. Then, using the scalar multiplication property twice, C T of U plus D T of V as desired. And that shouldn't be very surprising when we said that we define linear by our two operations of linear combinations. So now we're just saying that if you take a linear combination of vectors, you can break it up in terms of scalars and addition. So let's look at another example. Here we have two vectors e1 and e2, 1, 0 and 0, 1, and then two vectors y1 and y2 in R3, 1, 0, 2, 0, 1, 1. Let's suppose that T is a linear transformation from R2 to R3. R2 is the domain, R3 is the codomain, which maps E1 into Y1 and E2 into Y2. So first let's talk about that language, which maps E1 into Y1 and E2 into Y2. What that means is that if you take T of E1, its image is Y1. And T of E2 is Y2. Now it's important to think about these vectors, E1 and E2, and they're called E1 and E2 for a good reason. These are special vectors. Sometimes we call this the axis vectors, sometimes we call this the standard basis vectors, and we'll introduce what those terms mean later on. But E1, if we think about this in R2 space, E1 is just going one step in the x direction. And E2 is going one step in the y direction. So E1 is just going to correspond to a point x. And E2 is going to correspond to a point y. So we could say that the question says that we want to find the images of 3, 2, and then find the images of a general vector x1, x2. But if we think about this 3, 2, this E1 and E2 are building blocks of that 3, 2. We could write this as 3 E1 plus 2 E2. Again, any vector you can write as the linear combination of E1 and E2 as their building blocks. We could say that this is going to be 3 times 1, 0 plus 2 times 0, 1. The E1 vector corresponds to the x coordinate, and the E2 vector corresponds to the y coordinate, or the x1 and the x2 coordinate, if that's what we're thinking about. And you can always break down any vector like that into the axes vectors, or the standard basis vectors, these EIs. Now that I can do that, and I can write 3, 2 as a linear combination of those vectors, then we can say that T of 3, 2 is the same thing as T of 3E1 plus 2E2. And then using our properties of linear transformations, I can bring the constants out and do the additive property, and I get 3TE1 plus 2E2, 2T of E2, which will be 3 of T of E1 is Y1, T of E2 is Y2, and we know what those vectors are. That's going to be 3 times 1, 0, 2, and 2 times 0, 1, 1, and we can add those together, getting us 3 times 1 plus 2 times 0 is 3, 3 times 0 plus 2 times 1 is 2, and 3 times 2 is 6, plus 2 times 1 is 8. And that is our image of 3, 2 under T. Let's do that in general for any vector x1, x2. Before we do that, let's take a look at the picture here. Here is the picture that we drew before. Here's E1. Here's E2. It's going 1 unit in the x direction, 1 unit in the y direction, or the x2 direction. And here is our vector that we were looking at, 3, 2. And note that we thought about that as building blocks of those two vectors before. We could think about this as 3E1 plus 2E2 is that vector 3, 2. And we are translating that to something in R3. Note that in this picture we have this vector right here is T of E1. And here is T of E2. And in a very similar way, those new vectors are building blocks that I could write as a linear combination to get this new vector out here, which was the vector 3, 2, 8. Or that was the vector 3 T of E1 plus 2 T of E2. Everything is transformed into R3 in some way, in this case on that plane that we're looking at. So let's think about, in general, a vector x1, x2. Here we have T of x1 E1 plus x2 of E2 is going to be equal to x1 T of E1 plus x2 T of E2. And again, doing the same kind of thing here, this is x1 y1 plus x2 y2, which will be equal to x1 times the vector y1 plus x2 times the vector y2, which was 1, 0, 2, and 0, 1, 1. So in general, an image of this vector will be 3 dimensions, and it's going to be x1 times 1 plus x2 times 0, that's x1, x1 times 0 plus x2 times 1, that's x2, and then 2 times x1 plus x2. This is the range of this transformation. Every vector in the range can be written like this, in this form, for any values x1 and x2. So here we go, another example. We have a transformation T from R3 into R2, and that transformation is going to be given in a different way here. Here we say T of x1, x2, x3 of 3 variables. There's 3 inputs into that transformation. Give us 2 outputs. Those 2 outputs are given by the absolute value of x1 plus x3 and 2 plus 5 of x2. And we are going to show that T is a transformation, but T is not a linear transformation. So let's think about this transformation in a way that we're a little bit more used to. That is, T of the vector x1, x2, x3 is equal to the vector with 2 entries, absolute value of x1 plus x3, and 2 plus 5x2. Note again, this is T of x that we're talking about. To show that this is not linear, we are going to provide a counter example, an example where one of the following is violated. So what made a linear transformation is we know that if we have a linear transformation, T of 0 has to be 0, T of Cu has to equal C of Tu, and T of U plus V has to equal T of U plus TV. If one of those is violated, then we have a linear transformation. It's important to think about the logic of this real quick. So we say that if T is linear, then we know that T of 0 equals the 0 vector. The contrapositive statement to that is a true statement, and the contrapositive is if T of 0 does not equal the 0 vector, then T is not linear. And we could do that for all 3 of those cases. We could say that if T of Cu does not equal C of Tu, then T is not linear, and the same thing for the additive property. So to show something is not linear, we just need to show that something is violated, and all we need is one counterexample to show that it's violated. To show that it is linear, I need to show that these 2 things hold true. The T of 0 equals 0 was a result of that. So let's look at a counterexample here. We're going to look at the 0 vector property. T of 0 is equal to T of something in R3, 0, 0, 0. And using our definition of T, this will be the absolute value of 0 plus 0, and then 2 plus 5 times 0, which is the vector 0, 2, this is equal, and that's not equal to the 0 vector. And that means that T is not linear using the contrapositive result. We could have done that in a different way by looking at a different counterexample. In this case, looking at the scalar multiplication property. So here, we can just use one counterexample. Here we're going to use the value of C equals -1 and the vector U. Let's go back for a second. We know that, or we could say that all we need is one counterexample. This could be true for every single thing except for one example, and therefore it's not true. So you could find that it's true for some, but once you find that it's not true for one, then it's not true. So here's one example where it's not going to work. We're going to look at T of Cu and C of TU and show that they're not the same. So first let's look at T of CU. T of negative 1 times 1, 1, 1 is negative 1, negative 1, negative 1. And that's going to be the absolute value of negative 1 plus negative 1 is the absolute value of negative 2, which is 2. And then 2 plus 5 of negative 1 is negative 3. So here is T of CU. Let's do the same thing where this time I do T of U and then I multiply by that scalar. Here the scalar is on the outside negative 1, T of 1, 1. Scalar is on the outside, and I'm going to take the absolute value of 1 plus 1. That's going to give me 2. All's good. And then I'm going to have 2 plus 5 times 1 is 7, times negative 1 is negative 7. And I forgot to put the negative in from that negative 1 before. So negative 2, negative 7. In fact, both are incorrect, but really all we need is just that they're not the exact same thing as T of CU. This is C of TU. And these things are not equal. Therefore, T is not linear.